In our motivating example for controller design to meet performance specifications, we saw a way of kind of mathematically or analytically characterizing constraints on design variables. What we're going to see here is that we can map performance specifications back to closed loop poles and locations of closed loop poles in the complex plane that satisfy these various different performance specifications. So remember, we're going to deal with generic second order systems that we've characterized like this, where again we have two closed loop poles, a pair of complex conjugates, and they are characterized either by a real part and an imaginary part, or by a magnitude and a phase, where that phase is going to be written as the inverse sine of this damping ratio. And so that damping ratio is going to be related to this angle, but it's not equal to the phase. So remember that when we had, so I'm going to call this omega d just omega, and so that's the real part is sigma and the imaginary part is omega, and so that represents the location of these closed loop poles when we think about them in a rectangular sense. We think about them in terms of, again, a magnitude and an angle, then this omega n is going to represent the magnitude, essentially the distance from the origin to that closed loop pole. And this damping ratio zeta is going to be related to the phase. And so the way that we can characterize this is that before we derive that the damping ratio and the magnitude natural frequency omega n look like this. And so that creates some nice relationships characterizing these, and in particular, this also shows that there's this relationship here that we used actually in our motivating example that says that the real part is the product of these two factors. And so what's interesting about this and what's useful is the fact that all of these have different geometric interpretations. And so the reason why we use those is because if we look at our performance specifications, many of them can be interpreted as a function of mainly one of these variables. So for example, our rise time can be characterized as approximately 1.8, so it's a constant number, divided by omega n. And so if we want to achieve a rise time that's less than or equal to some desired rise time, so your performance specification, say, would be 1 second, so TR star, so that star represents desired, and so we'd say that we want the rise time to be less than or equal to 1 second, so that TR star would be 1 second. And so if we want this to be less than or equal to, when you solve for omega n, that means that omega n needs to be greater than or equal to this quantity. And so if TR star is 1, then it would just be 1.8. And so that indicates that we want all poles that satisfy this omega n greater than some number. And so let's just call it omega n greater than or equal to some, I'll just call it r. And so that r is, now what we're going to do is we're going to realize that this gives us a geometric constraint in the complex plane. So, and that's exactly what this first figure is demonstrating. So that omega n, remember, is that distance from the origin to the closed loop poles. And so the poles that satisfy either this expression or this one, whichever one you want to think about it, if this is the distance r, this circle represents the distance r away from here, then all of the points that are outside this circle, beyond, essentially with omega n values bigger than r, all of these out here satisfy this, this original time domain specification and gives us a rise time that's less than or equal to our desired value. So again, we started with this expression for how we compute the rise time from our characteristic, namely our closed loop transfer function. And so then what we did is we imposed that we wanted the rise time to be less than some value. That told us then, because there's this inverse relationship between TR and omega n, that we need omega n greater than some value. And so that means that there's going to be this semicircle in the left half plane that essentially says that any pole that lies here or here, anywhere outside that circle or semicircle, is going to achieve our time domain specs. Anything that's inside here is not going to achieve our time domain spec for rise time. So when we take a look at another of our time domain specifications, we can take a look at our settling time. And so here I've just chosen 1% settling time. So that's going to be 4.6, and then it's divided by either we've written it as zeta times omega n, but we've just reminded ourselves that this is actually the same thing as the real value. So now this is just going to be 4.6 over the real value. And so if we have a time domain specification that says that we want our settling time to be less than some value, say 5 seconds, then that means that corresponds, again, because these are inversely related, that means that our real value has to be bigger than 4.6 divided by our desired settling time. And so that means that, again, this has a geometric interpretation for a given value here. That's going to be a given point here that's going to create this vertical line beyond which all closed loop poles that fall over to the left side of this sigma value are going to achieve this inequality, which means that they give you a settling time that's less than what you want. And so that means that any poles that lie out here or here will give you achieve that time domain spec. Anything that's over here will not. And so both of these have a kind of a similar interpretation. So remember, like in this case, that the modes, where the closed loop poles are, our modes go like e to the pt, where p is the location of the pole. And so you can imagine the more negative this pole gets, the further you get in this direction, that means the faster these exponentials will decay. And so it makes sense then that our system will settle faster as we move our closed loop poles further to the left. For the rise time is related to simply just the magnitude of the distance. So this means that, yes, the real part is also becoming more negative, but it's also meaning that the imaginary part can actually help to achieve that rise time as well. So it's actually the whole distance from that pole, not just the real value. Our final one that we can use is that we can, from an overshoot criteria, so if we want the overshoot to be less than some value, then that means that given this number, we can go ahead and compute the zeta value that corresponds to that overshoot. And if we want this to be overshoot to be less than or equal to, then that ultimately means that our zeta value needs to be greater than or equal to some value. And so what that looks like in our geometric interpretation, this becomes a little bit trickier in this case, but it's just important to remember that for poles that are on the imaginary axis, the zeta value is 0. And for poles that are on the real axis, the zeta value is 1. And so zeta just goes from 0 to 1. And so as you increase zeta from 0 to 1, you move from a direction that's pointing along the imaginary axis directly up to a point that's pointing directly this way. And so it's related. Essentially, it doesn't move linearly, but it moves with the sign, or the inverse sign. But the idea here is that if zeta gets bigger, your poles essentially fit within a cone that looks like this. So that means as zeta gets bigger, this cone shrinks, and so it would become a more narrow cone like this. So if we had a time domain spec that said it had to be greater than some value, then that means that you're going to fit yourself within a narrower cone in order to satisfy that criteria, because bigger zeta values are closer to the real axis. And so, again, this kind of makes sense because zeta value, again, we call it the damping ratio, and that's really related to that how much oscillation you're going to get. And part of the reason why zeta is 0 here is because you have no damping if your poles are on the imaginary axis. That's an example of a system that will just continue to oscillate. And so if we want some amount of damping, some amount of decay that's kind of given by these exponential terms, you want to push push those poles closer to the imaginary axis to increase that zeta value. So again, our criteria, whatever you end up calculating your desired damping ratio to be, that needs to be that amount or bigger in order to satisfy your overshoot criteria, that's going to create this cone. And so typically our problems, and most design problems for control systems, may not be a single design criteria. So sometimes there will be multiple design criteria that you want to achieve. And so, for example, if you wanted to combine all three of these criteria exactly the way they're drawn in the blue curves, you would superimpose. And so we know that in this middle case, you need to be in this cone. For this settling time criteria, you need to be on this left-hand side. And for the rise time, you need to be beyond this semicircle. And so the way that you would characterize that is you need to superimpose them so that all of them overlap. And so what you can see is that if you move this one over here, you're going to draw that criteria. This section right here no longer satisfies this real value constraint, so none of this should be considered in your design scope. And so similarly, once you superimpose this semicircle on here, you get this semicircle. And so now none of this also should be in your design criteria. And so it's with this logic, this overlapping of these constraints, that you get essentially this overall shape where you can see that these are the different regions that are contributing to this, and they come from the three different design specs that we could consider. And so we're looking just for the regions that satisfy all three of these criteria, which is on the left side of all of this kind of more complicated blue line now. So all of that satisfies all three simultaneously. So this geometric interpretation is particularly useful when you have the potential of designing different controllers and possibly even different system dynamics in order to figure out what will work. And so one of the main tools that we will use is the overlapping of this geometric interpretation with our knowledge of the root locus. And so it's very easy to tell once you put your root locus down whether or not your root locus will either ever intersect in this feasible region, or if, for example, your root locus lives entirely over here and you never can reach these closed loop poles that will achieve your time domain specifications. And so this geometric interpretation is particularly nice to use when we're using it in combination with our knowledge of the root locus, which is where we're going next.